Section 5.5 is about the real numbers and their properties, and it's also about clock addition. If you look at the right side of the screen, I've inserted the definitions for just some of the main types of numbers. As we go through these definitions, which by the way the homework and the test are going to expect you to be familiar with, you're going to notice that many numbers fall into many different categories, unfortunately. So there is an overlap between a lot of the sets of numbers. So we'll start with the first definition on the side there, which is the natural numbers. And it says the natural numbers are the numbers 1, 2, 3, 4, 5, ... so etc. and so forth. These are the numbers we use for counting. So if I continue that ... pattern, you would see that 10 would be considered a natural number. 100, a billion would be considered natural numbers. All of the positive numbers that end in 0.0, so they don't have a decimal portion to them other than 0.0, those are all natural numbers. However, you do not see 0 in this set, and you do not see any negative numbers. You also don't see any decimals, like 1.5 is not a natural number. So just these positive, non-decimal numbers, non-decimal in that they end in 0.0, are the natural numbers. In the second row are the whole numbers. And whole numbers, you're going to see all the natural numbers, 1 through 5 and on, but also 0 is in the set. So whole numbers are all of the natural numbers plus the 0. So still don't see any negative numbers yet, nor do you see any decimals like 1.5 yet. So then the third row, the integers, which I've discussed in a previous video, ... -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, ... So now we've brought in the negative numbers into play. So these are all the whole numbers, plus the negative numbers now make up the integers. So I remember them as all the non-decimal numbers. In other words, 1.5 is not an integer. And you can see what I mean about the numbers fall into several different categories because the numbers 1 through 5 were natural numbers. 1 through 5 are also whole numbers, and they're also integers. And we're going to see in a second, they're also rational numbers, and they're also real numbers. So yeah, these numbers definitely fall into many different categories. The rational numbers are your fractions. Specifically, when you take one of those integers, one of those non-decimal numbers, and you divide them by another integer other than 0. And I have the textbook's definition of this on the side. It says a divided by b, where a and b are integers, and b on the bottom cannot equal 0. So pretty much what I just said, an integer divided by an integer, just so the integer on the bottom does not equal 0. That gives you a rational number. And we discussed this briefly in a previous video as well. And we showed in that video that when you take an integer and you divide it by an integer, it forms one of two types of decimals. It forms a decimal that either terminates, meaning it ends, or it repeats the same pattern forever. So these are your terminating or repeating decimals. The opposite of rational, of course, is irrational. The irrational numbers we discussed in the last two videos, and these, since they're the opposite of rational numbers, these are non-terminating, nor are they repeating. So they don't end, nor do they repeat the same pattern. They're just those random decimals that never end, no pattern to them. So these cannot be expressed as a quotient of integers. In other words, they cannot be rewritten as a fraction of an integer divided by an integer. So keeping these definitions in mind, I'm also going to add to it that the real numbers, like the title of this section, are when you take all of the rational numbers from a number line and you put them together with all the irrational numbers. So if you put all those decimals together, that makes up all of your real numbers. Pretty much all of the numbers we're going to work with in this course are real numbers. The only numbers that are not real you would work with in an algebra course, and those would be the imaginary numbers. And imaginary numbers would have that little lowercase cursive I. You might remember that from your last algebra course, but we're not going to worry about imaginary numbers or complex numbers in here. Real numbers are the biggest set we're going to work with in this chapter. So finally, looking at example 1, consider the following set of numbers. We got -9, -1.3, 0, 0.3 with a bar above it, meaning it's repeating, pi divided by 2, square root of 9, square root of 10. And it says to list the numbers in the set that are A, natural numbers, B, all the whole numbers, C, integers, D, the rational numbers, E, the irrational numbers, and finally F will be the real numbers. Now just be aware that the homework does have a pattern to it, where most of the time you're going to see 2 numbers under a square root symbol. One of those square root numbers, they're trying to trick you. One of the square root numbers actually reduces further so that it's a nice rational number, whereas the other square root number is not so nice. It's an irrational number. So clearly square root of 9 is the nicer one here, because if I take the square root of 9, that really just equals 3, meaning what times itself is 9 is 3. Whereas square root of 10, if I type that into my calculator, it's 3.16227766, meaning that it's irrational because there's no pattern to that decimal, and it does in fact go on forever. So square root of 9 is the nicer square root number because it equals 3. And it wants all of the answers as a set. Whenever in math it asks you to write answers as a set, that means that you need to draw curvy set brackets around your answers. So you'll need to type in those set brackets in the homework. You can use the keyboard, or if you click in the answer box, a template will appear where you can select the set brackets from. So that's your choice for how to get that answer into the homework. But A asks for all the natural numbers. Remember the definition for natural? These are the positive non-decimal numbers, like 1, 2, 3, 4, etc. So here, the only positive non-decimal number I see is 3. Which was represented as the square root of 9. So square root of 9, I would just leave it as square root of 9. Make sure you do not hit the space bar ever when you're typing this answer into the homework. Close your curvy set brackets, and that was your only natural number. B, list all the whole numbers. Well, I'm going to list the natural numbers plus 0. If you see 0 in the set, and we do, I put in my curvy set bracket in blue there. So here was 0, comma, square root of 9, since that represents 3. Those were all whole numbers. Next up, C, I'll do in black pen, the integers. So you're going to write all your whole number answers plus the negative non-decimals. So I'm going from left to right in the set. -9, yep. Check, that's an integer. It's a negative non-decimal number. 0 was an integer. It's a whole number, and it's not a natural number, but it was an integer and it was a whole number. Let's see what else is an integer. 3, which is represented by the square root of 9. So -9, 0, square root of 9 are the only non-decimal numbers here. I'm going to switch back to red pen for D, the rational numbers. These are your fractions, or they could be rewritten as a terminating or repeating decimal. And actually, you know what I'm going to do just to make sure I get them all, because the rational numbers is usually a huge set of answers, and I'm worried I'm going to miss 1 or 2 of them. So I'm going to come back to part D, and I'm actually going to do the opposite of the rational numbers, which is the irrational numbers first. Once I've identified the irrational numbers, all the numbers that are not irrational will fall into the rational numbers set. So looking at E, irrational numbers, these are the numbers that produce those random, never-ending decimals. They have no pattern to them. They do not repeat the same pattern. So usually in the homework, these are the numbers that have a pi in them. They have the number E involved in them. And they're also the more complicated square root numbers, the square roots that do not produce a nice integer answer. So keeping that in mind, I see a pi number right here. I see pi over 2. And sure enough, if you type in pi divided by 2 into your calculator, you're going to see that it does represent a random, never-ending decimal. So this is still a set, so I need those set brackets. Pi over 2, comma. And out of the 2 square roots I'm given, the not-so-nice square root is going to be my irrational number every time. So that's square root of 10. And again, if you wanted to check that answer, type it into the calculator, press enter. Yet again, you're going to see that just random, yucky, never-ending decimal. So pi over 2, square root of 10 are my only irrational numbers. If I X those out in blue, everything that's left is a rational number. So going back to D, I have a negative 9 left, comma, we got negative 1.3. Yeah, negative 9 is technically a terminating decimal because it can be written as negative 9.0. Negative 1.3 is also terminating. 0 is technically terminating decimal because you could write it as 0.0. I got the repeating decimal because I got 0.3 repeating with the bar above it. And square root of 9, which represents 3, which is a terminating decimal of 3.0. So every single number that you do not have listed as an irrational number, mush it all together, it's part of your rational numbers. And then the easiest part of this question of all is part F, the real numbers. You're just going to rewrite all the numbers in the original set back again because they're not going to deal with imaginary numbers in this textbook, so we don't have to worry about that. I abbreviated numbers #'S, so rewriting the whole set back again, negative 9, looking at the original question, negative 1.3, 0.3 repeating, pi over 2, square root of 9, and square root of 10. And again, please keep in mind when you're typing this into the homework, you do need set brackets around it, but never ever hit the space bar. You do need commas, though, between all of your entries, your elements. We call those numbers. Example 2 highlights the clock addition part of this section. So it says, shown in the figure are an 8-hour clock and the table for clock addition in the 8-hour system. It's an 8-hour system because there are 8 total numbers on this clock when you include 0 in the count, because it's 0 and then 1 through 7. All these clocks always start with 0, so it's not a typical clock like you would hang on a wall here. And the way that the table works that's beside it is the headings are on the left and the right sides. They show you that you're adding, meaning you're going clockwise. In the upper left-hand box there, it's a plus symbol circled. We got the row headings that are in bold on the side, which are all the hours on this particular clock, 0 through 7. You also have the same exact numbers as column headings on the top. So like for example, if I wanted to do 2 plus 7 on an 8-hour clock, resist the urge to write 9. So on this clock, visually, I'm starting at 2 o'clock. Adding 7 means I'm going to go forward clockwise 7 hours. So here we go. 1, 2, 3, 4, 5, 6, 7. Land you at 1 o'clock. So 2 plus 7 equals 1 in this strange 8-hour clock system. But you never thought you would write that. 2 plus 7 equals 1. If you wanted to use the table instead of the picture, it's a lot quicker once you get the hang of it. So the number you're first given, which was a 2 in this case, you look up in the rows on the left-hand side. So here's the 2 label. You're adding 7. The second number, the number you're adding, is what you look up on the column heading. So here's the 7. And then you just simply see where those numbers intersect at. So if I draw a horizontal line here and a vertical line here, sure enough, they land on the number 1. I drew that a little bit too dark. There we go. Now we can see it better. They land on 1. Let's try another one. If I wanted to do 5 plus 6, it no longer equals 11 in this clock world. If I wanted to use the table, the number 5 is first. Here's my 5 label. I'm adding 6 to it. Here's my 6 column label. And they would intersect at 3. So 5 plus 6, on an 8-hour clock anyway, equals 3. If I wanted to check my answer using the picture, we're starting at 5 o'clock. Go 6 hours clockwise. So 1, 2, 3, 4, 5. Yep, 6 lands me, sure enough, at 3 o'clock. And this is actually a really long question, so I've copied and pasted the original picture of the table onto the next slide or two. But A, B, and C I was able to fit on this slide at least. So part A says, how can you tell that the set 0 through 7 is closed under the operation of clock addition? There's a lot of vocabulary with this type of a question in the homework. So really, you're just going to recite back the definition of closed. It might even be a multiple choice question, honestly, in the homework. So closed in mathematics means that all the possible answers you could potentially get are back in the original set. So if my original set is the numbers 0 through 7, when I look through all the possible answers that I'm circling in blue right now in the table, I better only see the numbers 0 through 7. So in other words, if it's closed, I'm not going to see an 8, a 9, or a negative number. So as I skim each row, sure enough, I'm only seeing 0 through 7. So yes, this is a closed set. Wording it kind of similar to how the homework is going to word it, I would say, because this is how can you tell that the set is closed? Well, I can tell that the set is closed because all the entries in the table, in other words, all the answers in the table, all the entries in the table are all the possible answers in set brackets, we call those elements. So instead of numbers, elements. So are all elements of the original set. If the word elements bothers you, just pretend they're saying the word numbers. So all the entries in the table are all numbers of the original set. And that's pretty much the definition of the word closed in mathematics anyway. Looking at B, it says to verify the associative property. So 4 plus 6 plus 7 equals 4 plus 6 plus 7. So the associative property, if you compare what's on the left side of the equal symbol to what's on the right side, they're similar in that they both have the same numbers in the same exact order. They both have a 4 first, then a 6, then a 7. The only thing that's different is they scooped up the parentheses that were around the first pair of numbers, that were around the 4 and the 6, and they dropped them so that the parentheses were around the last pair of numbers, the 6 and 7. So that's all the associative property in mathematics means. It means that when you're adding, and even multiplication, this is true too, if you move parentheses around from the first pair of numbers to the last pair of numbers, who cares? You're going to still get the same exact answer regardless. And when they say verify, it just means prove that this is true. So I'm going to simply use the table to figure out the answer to both sides of the equal symbol, and I should get the same exact answer if I'm verifying. So starting with the left side of the equal symbol, in fact, I'm going to draw a little divider below the equal symbol. we would do parentheses first. So I'm going to do the 4 plus the 6 first. And you can ignore this plus symbol in the middle. We know we're going to be plussing every time with the clock addition. So 4 plus 6, so I look up 4 in the row headings and 6 in the column headings. And 4 plus 6, they intersect at 2. So 4 plus 6 in this 8-hour clock is 2. Now we got to add the 7. Bring down the 7. Step 2, we're going to do 2 plus 7, which coincidentally we already did up here. It should equal 1, but we'll do it again just to really verify it. So 2 plus the 7 intersects, yep, at 1. So we get an answer of 1 on the left-hand side. We better get another answer of 1 on the right-hand side if we've done it correctly. We do parentheses first again, so now in parentheses is 6 plus 7. So 6 plus the 7 intersects at 5. Bring down the 4 and the plus symbol that are in front. Now I'm going to do 4 plus 5. So 4 plus the 5 lands me on 1 again. Yay! So I got 1 equals 1. I got the same answer on both sides, so I have verified the associative property holds true. C. What is the identity element in the 8-hour clock system? And remember, if the word element bothers you, for this example, all of our elements are numbers, so you can pretend the word element really says number. So what is the identity number in the 8-hour clock system? Well, whenever you're adding normal numbers or even clock addition, the good news is that the identity number will be the same. The identity number will always be 0. Final answer. Why 0? Because identity number means what, when you add it to a number, gives you back that same exact number. So if you check your table, pick any number out from this table, and if you add 0 to it, the identity number, you're going to get back the same number again. So like 1 plus 0, 1 plus 0, yep, it intersects at 1. 2 plus 0, 2 plus the 0 intersects at 2. 3 plus 0 is 3. 4 plus 0 is 4, and so on and so forth. You can go ahead and feel free to check the rest of the table, but if you add 0 to any number, it's going to give you back the original number. So in addition, 0 will always be the identity number. What about multiplication? What's the identity number for multiplication? Well, what, when you times it by a number, will give you back the same number again? 1. So the identity number for any kind of timesing would be 1, and that's always going to be true. Still the same exact question. Remember, this is a longer section, a longer question. So I just copied and pasted the same 8-hour clock on the top of the screen. We're on part D. It says to find the inverse of each element, in other words, each number, which I'll abbreviate with a hashtag, in the 8-hour clock system. Inverse means that your answer is the identity number. And we just said with addition that the identity number will always be 0. So what, when you combine it with each number, will give you a final answer of 0. So this is the only type of question or part of this clock addition question where you're always going to work backwards with the table. So let me show you what I mean. So first, we're going to find the inverse of 0. So you're going to point on the left-hand side to what you want to find the inverse of. So first, I want to find the inverse of 0. and then you're going to move your hand to the right until you land on the identity number, which is also 0. So move your hand to the right till you land on 0. I land on 0 right away. Here it is. And then step 2, look up to the tippy top column heading, and it's 0. So the inverse of 0 is 0. Let's try another one. 2 steps. Now we're going to do the inverse of 1. So remember, you look up from the rows on the left-hand side what you want the inverse of. You move your hand to the right until you land on 0. Then step 2, once you land on 0, you look straight up to the top, and the column heading is 7. So the inverse of 1 is 7, because 1 plus 7 equals 0, equals the identity number. What about, I'm going to abbreviate inverse INV here, the inverse of 2. Well, here's 2. Move your hand to the right till you land on 0. Then step 2, look up to the tippy top, and 6. The inverse of 2 is 6, because if you check going forward, 2 plus 6 equals the identity number of 0. Now we need the inverse of 3. So here's 3. Move your hand to the right till you land on 0. Step 2, look up to the top. The inverse of 3 is 5, because 3 plus 5 equals 0, if you wanted to check it going in a forward direction. Now we're going to do the inverse of 4. Here's 4. Move your hand to the right till you land on 0. Now look up to the tippy top. The inverse of 4 is itself. It's 4 back again. Now, let's try to create some room over here. The inverse of 5 is next. Here's 5. Go to the right till you land on the identity number of 0, and go up to the top, and we get 3. The inverse of 5 is 3. Now let's do the inverse of 6. Starting at 6. Move your hand to the right till you land on 0. Go up to the tippy top, and we get 2. The inverse of 6 is 2. That's a sad looking 2 I just drew. Let's try that again. Inverse of 6 is 2. There we go. And finally, the inverse of 7. Here's 7, go to 0, go up to the top, and bam, we get 1. Inverse of 7 is 1. So we did the inverse of every single number, every single element, as they would say in the homework, in the original table. And finally, part E, verify the commutative property. The commutative property for addition and multiplication means that you can change the order of the numbers and it doesn't matter. You're going to get the same exact answer. So 5 plus 6 should equal 6 plus 5. Let's check using the table, both sides. We're back to verifying, so we're back to moving in a forward direction on the table. So here's 5. We're going to add 6, and they intersect at 3. So 5 plus 6 is 3. Now let's do 6 plus 5. We should get another answer of 3 if we're doing it correctly. So here's 6 plus 5. And sure enough, we land on 3 again. So we have verified because we got the same answer on both sides of the equal sign, that the commutative property holds true even with clock addition.